In part one, we introduced the concept of taking the divergence of a vector field. What we're going to do now is look at the mechanics of how would you actually do this in Cartesian coordinates. Okay, so we're going to look at a differential volume in Cartesian coordinates, which will be a cube beside delta x, delta y, and delta z. We're going to assume we know the electric flux density field at the center of this cube and how that flux density changes with respect to x, y, and z, so that we can then get an estimate of the electric flux density fields on the 6 faces of the cube. We will then add up the integral of d dot ds on those 6 faces, divide by delta v, and take the limit as delta v goes to 0, and we will have an equation for performing the operations of divergence in Cartesian coordinates. Now, if you wanted an equation for performing the divergence in spherical or cylindrical coordinates, you'd go through the same process, but you would start out with the differential volume element in those different coordinate systems. Looking at this cube, let's call this the front face and the opposite side the back face. And now what we want to do is see how we're going to estimate the electric flux density field on the front face and the back face, knowing the electric flux density at the center of the cube and how it changes with respect to x, y, and z. So here we have a plot of the electric flux density field in the x direction as a function of x. So let's assume the center of the cube is at x sub 0, and we know the value of d sub x at x sub 0. And we also know the slope at x sub 0. Okay, so this line is the slope of the part of d sub x with respect to x at x sub 0. So if we move a distance delta x over 2 from x sub 0, we're on the front face of our cube, and if we move a distance delta x sub 2 to the left of x sub 0, we are at the back face of the cube. So our estimate of d sub x on the front face will be this value right here. And our estimate of the value of the electric flux density field on the back face in the x direction will be this value right here. The actual value of d sub x on the front face is right here. So this distance here will represent the amount of error in our estimate on the front face. And on the back face, this is the actual value of d sub x on the back face. So this distance will represent the error in our estimate on the back face. Of course, as delta x gets smaller and smaller, our error also gets smaller and smaller. So now let's look at these two right triangles. So this level right here is the value of the electric flux density field in the center of the cube. So to estimate the value at the front face, we add to it this distance right here, this side of the triangle, which will just be the slope of this line times this side of the triangle, which is delta x over 2. So our estimate for the electric flux density field on the front face of the cube, this d sub x at x sub 0 plus delta x over 2 will be this value right here, d sub x at x sub 0 plus this side of the triangle, which is the rate of change of d in the x direction with respect to x times delta x over 2. Okay, now similarly, our estimate of d sub x on the back face of the cube, this value right here, will be the value of d sub x at the center of the cube minus this side of our right triangle. Okay, so this side of our right triangle will be our slope times this side of our right triangle. So d sub x at x sub 0 minus delta x over 2, the back face of our cube will equal the value of d sub x in the center of the cube minus the rate of change of d sub x with respect to x times delta x over 2, this side of our right triangle. So now we have a procedure for estimating the electric flux density field on the 6 faces of our cube. So again, this shaded face we'll call the front face, the opposite side the back face. Let's call this face the right face, the opposite side will be the left face, and let's call this the top face, and the opposite side being called the bottom face. So the integral of d dot ds around the cube will be the integral of d dot ds on the front face plus the integral of d dot ds on the back face plus the integral of d dot ds on the left face plus the integral of d dot ds on the right face plus the integral of d dot ds on the top face plus the integral of d dot ds on the bottom face. So what we're going to do is first determine the sum of these two integrals, and we'll see then we can infer the second and third lines here from our result for the first line. Okay, so let's look at the integral of d dot ds on the front face first. Okay, so this surface on the front face orientation is in the a sub x direction. Okay, so this integral will become d sub x on the front face times delta y delta z. So when you take the dot product, you're just going to get the value of d sub x in the x direction times the surface area of the front face, delta z, delta y. And using the technique we just looked at, our estimate for d sub x on the front face is the value of d sub x in the center plus the rate that d sub x is changing with respect to x times the distance from the center of the cube to the front face, which is just delta x over 2. Okay, so now our estimate of d dot ds on the back face is going to equal minus d sub x on the back face times delta y delta z. And the reason we get the minus sign is that the surface element on the back face is pointing in the minus a sub x direction. So our estimate of d sub x on the back face is the value it has in the center of the cube minus the partial of d sub x with respect to x times the distance from the center of the cube to the back face. And looking back here, this is our estimate of d sub x on the front face, and then we still have it times delta y delta z. So now let's add these two. Okay, so we see we're going to have a d sub x 0 delta y delta z minus a d sub x 0 delta y delta z, so those cancel. And the second terms here with the minus times a minus will add, so the result will be the partial of d sub x with respect to x times delta x delta y delta z, which is just the partial of d sub x with respect to x times the volume of our cube, delta v. Okay, so now if we go back to our equation for the integral of d dot ds around the whole cube, we see for the sum of these first two terms, the result is partial d sub x with respect to x times delta v. And so you could go through the same details or just from inference figure out that the integral of d dot ds over the left face plus the integral of d dot ds over the right face is the partial of d sub y with respect to y times delta v, and the integral of d dot ds over the top face plus the integral of d dot ds over the bottom face is the partial of d sub z with respect to z times delta v. So let's rewrite then the integral of d dot ds over the surface of the cube is equal to the partial of d sub x with respect to x plus the partial of d sub y with respect to y plus the partial of d sub z with respect to z times delta v. Okay, so now let's go to our definition of the divergence of d. So we have the integral of d dot ds over the surface of our cube. So now we're going to take that, divide by delta v, and take the limit as delta v goes to 0. Okay, so the divergence of d equals the limit as delta v goes to 0 of the integral of d dot ds over delta v, which is equal to the right-hand side here, which when you divide by delta v, you'll just be left with partial d sub x with respect to x plus partial d sub y with respect to y plus the partial d sub z with respect to z. Now let's see why we write the divergence as del dot d. So we're going to introduce the del operator. Okay, so the del operator is given the symbol del, and it's equal to the partial with respect to x times a unit vector in the x direction plus the partial with respect to y times a unit vector in the y direction plus the partial with respect to z times a unit vector in the z direction. So del dot d will just be the dot product of the del operator with the dot product of the electric flux density field. Okay, so here's our del operator. And let's write out our electric flux density field in component form. And let's go through the distribution of these two terms. So ax dot ax is 1, so you'll have a partial d sub x with respect to x. ax dot ay is 0 and ax dot az is 0. Go to the second term. ay dot ax is 0, ay dot ay is 1, so you have a partial of d in the y direction with respect to y, and ay dot az is 0. Final term, az dot ax is 0, az dot ay is 0, az dot az is 1, so you'll have a partial of d in the z direction with respect to z, and of course that's equal to the charge density.